for Dr. Wagner, Mr. Barrows, and Mr. McGinnis. In y'all's prepared testimonies, y'all emphasize the need for DOE to support research that will make high-assay, low-enriched uranium. Are you calling that HALEU? What do you?
HALEU or
HALEU, okay.
high-assay LEU.
Okay, perfect.
Terms of art.
Fuel available for advanced reactor technologies. So what is HALEU fuel, and why is it needed to advance the next generation of reactor technologies? And Mr. Bowers, we'll start with you.
Thank you very much. So we start with the definition, right? All existing light water reactors operate on fuel enriched uranium that is at a enrichment of less than 5%, 4.8, 5.1, and down from there. The military needs for uranium start at, as well as some test reactors within the United States, start at 20% and go up. So there's this no man's land, this range between 5% and 20% enrichment that's called high-assay, low-enriched uranium. Several of the advanced reactors are looking to use high-assay LEU for their reactors. That enables higher burnups, improved efficiencies, longer periods of time between outages. So there are a lot of benefits to using it.
So why hasn't that been done heretofore?
The demand for uranium, demand for product, has been driven by what the market currently requires, which is light water reactors at 5%. So no one's going to build a factory to make something that makes 8% if no one's going to buy it. And the needs for the test reactors is relatively small, and so that's been able to be supported by DOE, Y-12, and other sources within the U.S. I'll stop there.
Mr. McGinnis?
Well, I don't want to add more to his technically sound description, so let me just describe briefly the demand. We actually have, there is no high-assay LEU commercially available on the planet right now. The majority of the new innovative
not even for testing?
There was.
Oh, you're saying commercially available?
Commercially available.
Okay.
So no U.S. company that is looking to bring in their reactor right now, they have no high-assay LEU fuel. They have no fuel for their design. And that creates a great risk. The closer they get to trying to deploy, they can't sustain that risk, not knowing there is none. That doesn't mean that enrichment facilities can't move forward when they see enough of a market, a customer demand, but we have a chicken and the egg here.
Is that a short startup time?
Not that short. Be able to get this established with the high-assay LEU, you're talking a couple of years at least. So it's not going to be immediate. However, that's where I think the Department of Energy is in a unique position to help spur and support at least the laboratory scale, if not a little bit larger scale, for the demonstration of high-assay LEU for these new reactors to provide the confidence. We have micro reactors. Many people may not realize this. They may be coming in as early as 2021, 2022. These are reactors that will need high-assay LEU.
Are you calling SMRs micro-reactors?
Micro-reactors are smaller than SMRs, so micro-reactors, depending on the definition, in general, it's 1 to 5 megawatts electric. Some define it up to 50 megawatt, but in truth, most of the micro-reactors are about 1 to 5 megawatt electric. But 1 megawatt electric, that supplies power to 1,000 homes. So that's not insignificant. So we have a very near-term need for the ability to provide confidence to these new innovators in the markets that high-assay LEU will be available when needed.
Okay, thank you. Dr. Wagner?
I would just add that some of the accident-tolerant fuel concepts for the existing light water reactor fleet are also looking at enrichment above 5%, more in the lower range, 5 to 8%. So some of those concepts also have a need here for this fuel as well. Whereas the advanced reactors are primarily looking at right close to 20 weight percent. With the support from the department, we're actually taking several steps, but we need to do more. Some of that is initially recovering high-enriched uranium from spent fuel, such as our EBR2 fuel.
And that's what France does?
No, France reprocesses commercial light water reactor fuel, so 5% and below. So what we're doing is we're recovering the uranium from our old EBR2 spent fuel and downblending it to 20%. So there are some sources there for the very near term that might support one of the microreactors, for example. But we've got to get a longer supply out. There's other opportunities to increase that in terms of recovery from other spent fuel sources, but long term we'll need an enrichment capability in this range.
All right, thank you. With your indulgence, Mr. McNerney, I'm going to ask Mr. Bowers one more technical question. You talk about systems that can shut themselves down. You evacuate the helium, you move off the coolant, and then you watch that system as it basically self-regulates. How in the world does it do that?
I did start out by saying I'm an engineer and not a physicist, but I can take a stab at it.
Okay.
Which is that there are within the uranium there are what's called resonances, and in these resonances at certain temperatures, rather than emitting neutrons, the uranium absorbs the neutron. So when you get to a particular temperature, you've got neutrons being absorbed instead of being expended, and that's basically what fuels the reaction. So as you
so that's not an implosion in of itself. What happens when they absorb those neutrons?
It returns to a more stable state. And the temperature goes down within the.
Do you have a temperature
core
range for us? Do you know what that temperature range is?
It's between 1,000 and 1,100 degrees centigrade. Our reactor operates around 900 degrees C, and the outlet temperature on the helium is approximately 750 degrees C.
And time frame, is that 15 minutes, 15 hours? What's the
a cycle like that is predicted to be on the order of 25 to 35 hours, and so each a day or 2 days you'd see it cycle up and cycle back down again, and it would continue in this kind of state for weeks if necessary until power was returned and you.
So if you restore to arrest that cycle, for lack of a better term, or to restore it to its original.
To arrest the cycle, insert the control rods is the way that we would accomplish that, and we actually have two separate, in our particular design, two separate banks of control rods, one for operation and trimming performance, and the other for shutdown.
Well, I want to ask you why that is, but I won't. So the gentleman from
Defense in
California.
depth.
The gentleman from California